Welcome back, and now we're still going to talk about function properties, but we're actually going to try and apply the things that we've learned in a little different way. So you might want to read this example, and then you can laugh or chuckle or just shake your head and say, "Oh my goodness!" But so a while ago, cell phone plans had just a base price for a set of minutes, and you were charged for any minutes that you went over. Now we have unlimited, right? And then if you wanted to text, that was an additional fee, which we're not going to worry about. But suppose that a particular plan for a cell phone charged $80 per month, and that gave you 250 minutes. And then if you went over 250 minutes, it'd be 5 cents per minute over the 250. So then the question is, how much would it cost if you used 120 minutes, 200 minutes, 300 minutes? Now, this, I imagine you might be able to solve quite quickly. So you say, okay, well, 120 is less than 250, so this is just the $80. If it was 200, that's still under the 250, so this is $80. But then the 300, right, that's over, so you'd be charged the $80 for the 250, and then you'd be charged 5 cents for the remaining 50 minutes. So, and then if you do this, you figure out your bill would be $82.50, assuming I did my arithmetic correctly there. So 50 minutes over and it's only $2.50. I mean, now it's like, that's not bad. But keep in mind, texting is not included, nor data. So have fun paying those extra fees. But when we were doing this process, we were actually using a piecewise function. We just didn't realize it. And so all that means is that we have a function that's defined in pieces. So we have kind of one condition for one range of value, or for one domain, and then we have another function for a different domain. So when we construct a function like this, and you've seen this before, I think this was pulled from an activity a while ago in 1.3 or something like that. But this, we just gave you the graph before. We didn't give you the algebraic form. And so this is what a piecewise function would look like. So we call it, again, it has different pieces. So when x is less than 0, it follows this function. When x is between 2 and 0, inclusive at 0, then it's that function. If it's more than 2, then it's that function. Okay, so then now let's imagine for a minute that I didn't have the graph. Okay, so I'm going to just scribble that out. How would I answer these questions? Well, f of minus 1, now, again, I can still use a graph and say, oh, it's going to be 0. Yeah, but let's maybe just see if we can verify it algebraically. So this would say, okay, I need to use -1. Which piece does -1 fall into? Oh, it's less than 0, so I'm going to use this first piece. So instead of x, I'm going to put in -1 and then +1 and square that. Because again, I'm using that first piece. I'm not using any of the other pieces. So then I just get out 0. Oh, that was easy enough. And we can verify that with the function. Okay, we can unscribble all that. Okay, but again, we're going to try algebra first, verify with the graph. Second one, 0. Okay, which piece does 0 fall into? Well, there's 0 there and 0 there, but we have the equal in the second piece, so I'm going to just use that function, and well, I can't really put in 0, but I get out -4. Okay, and then verifying at the function, when x is 0, yep, I have -4. Okay, f of 2. Okay, f of 2, again, I have to figure out which piece I'm going to use. Oh, wait, 2 isn't defined, right? So this one I would just say undefined. And again, we can check with our graph. Where's the closed dot at 2? There isn't one. So, crap, can't go any further. Now the next one, f of 50, that one is a little different because we can't see it on the graph, right? So we can't verify this graphically, but this is where the function comes in useful. I can say, well, okay, which piece is 50 in? X is 50? Nope. X is 50? Nope. X 50 is bigger than 2? Yep, so I'm going to use this one, and I'm just going to say, instead of x, I have 50, so I get 50. Boom, done, drop the mic. Okay. So, piecewise functions, figure out which piece you're in, go forward. Now, in addition to using a piecewise function, you need to be able to generate one. So both graphically and algebraically, and that's what we're going to focus on in the rest of the video here. So graphically, it really is as simple as let's graph each of the pieces, just making sure that we're in the right domains. So I'm going to make a little sketch here. I'm going to do like this, and I think I should probably number out to like 5 in each direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Well, I don't need to go. I'm not going to need to go down anymore. Okay, so to graph this first piece, right, I need to take some points in this region. So if you needed to make an XY table for the first piece, you could do, okay, so -2 is in the domain, as is -3, and you could punch these in, 4 and 6. So I need to maybe go up 1. But anyway, I can plot this. I'm going to plot this in green. So at -2, I have 4. And I have a closed dot there because I have inclusion. And at -3, I have 6. So this is a line, so I just need something like that. Okay? For the next piece, x squared, we kind of know what that looks like, right? And so that's going to be our basic quadratic. And I need to stop when x is 2, so something like that. And I'd have an open dot technically there, but I'd have the next piece looking like that. Okay, and for the last one, I'm going to do this. So again, if you need to make a little table, because this would be a line, slope 1, shifted up 1, but we need to begin at, say, 3 and 4, because we'd have we could do 2, but we'd have to do it. I'm just going to make an open dot note there. But then putting this all in, this is going to be 4, 5, and 3. So at 2, I'd be at 3, which is right there, and then there and there. So I'd have the next piece looking like that. Okay, so a little bit of a gap there. Now the last question is it continuous? This one, so the idea of continuous is that you can draw it without lifting up your pencil. So imagine you're kind of taking your pencil and drawing this. Yep, I can do this part just fine. And then, to get to the next one, I have to pick my pencil up and then start all over again. So this one is going to be, no, it is not continuous. I need to lift up my pencil. Okay? All right. So the reason we talked about that cell phone plan at the beginning was just to be able to do this word problem, and I know you love word problems. Okay, we want to construct a piecewise function. Okay, our scenario is the same. So what I'm going to do is, I'm not given any variables. I should probably define some variables. So I'm going to use C of M, and this is going to represent the cost in dollars for M minutes used. Okay, so C of M as a function, it's going to be a piecewise function with 2 pieces, right? Because we know under 200 or 250 minutes and under, right, you're charged $80. So we would say the first thing is it's going to be 80 if M is less than or equal to 250. Okay, and then we know that if M is bigger than 250, then we're charged the $80, and then we tack on 5 cents for any minutes over 250. Now the way we represent that minutes over 250 idea is going to be M minus 250, because again, if we're in this range, like if M was 300, then I would want this whole thing to be 50. So then in order to get it to be 50, if M is 300 itself, is to take away 50 from it. Okay, so pay attention to this little part. That can be the trickiest part of the entire problem. And that's going to wrap up piecewise functions. So you have to be able to evaluate, produce, both graphically and algebraically.